Maybe what we should do is just try to finish the particular problem. And that is CH4 plus, let's see, C6H12O6 solid plus 6O2 gas yields 6CO2 gas plus 6H2 liquid. But what was delta H for this reaction? It was, I think, minus 2802.5 kilojoules, correct? What you had? Yeah. From yesterday. No, it didn't. All right, so we can do a delta U calculation. You know, delta U is going to equal delta H plus Q. Oh, not delta Q, delta H plus W. In other words, Q plus W. So all we have to do is figure out what the work involved in this is. So there are different ways of figuring out the work, you know, at different levels of detail. And so the work term, you know, options for that, from fastest to slowest. The fastest is, we just looked at delta N of gas, you know. The fastest is delta N of gas. Delta N of gas is equal to the total moles of gas in the product minus the total moles of gas in the reactants. And so here, if you look at how many moles of gas do we have in the products? 6. And reactants? 6. And so if delta N of the gas is 0, then the work is P delta V. And we assume that since there's no change in gas, that delta V is pretty close to 0. And therefore, the work is 0. And so the fastest would be that delta U is equal to delta H. But what are we ignoring? What are we assuming here? You know, we assume that liquids and volume, liquids and solids are negligible. What else do we assume? We assume that O2 and CO2 are ideal. All right, then the next is more detail. The next we won't assume, you know. And so let's see, this will be A, from fastest to slowest. So A is delta N of gas only. This is what Petrucci does, delta N of gas only. B is, we'll account for solids and liquids. We'll still assume that the gases are ideal. All right, in this case, we could calculate, you know, V initial. V initial is the volume of C6H12O6 solid plus the volume of O2. Okay, the volume of C6H12O solid is 180.12 grams. This is a mole, right, of C6H12O6. And then the density is 1.54 grams per milliliter. 1 milliliter has 1.54 grams, 25 degrees C. And then we'll convert it to liters. So, 1,000 milliliters per liter. Since I didn't finish this problem the other day, we might as well just finish this to get a good idea of what's going on here. And so that's 180.12 divided by 1.54 divided by 1,000. And we got 0.119, 0.1169 liters. Okay, now let's do the volume of O2. The volume of O2, we have 6 moles of O2. And then we know the molar volume. It's 24.7 liters per mole. This is at 1 bar and 298 Kelvin. And so that's 6 times 24.7 is from an earlier calculation. That gives us 148.2 liters. So, do you see that Petrucci ignored the solid, because the solid, does it have much volume? No, I mean 0.1 liters. So much volume there. And so, but altogether, we'll just add these up. If we add these up, we're going to get 148.3 liters, 0.31 liters. And so our initial volume is 148.31 liters. Then let's continue on with this. Then our final volume is going to be the 6 moles of CO2. So we'll need the volume of the CO2 plus the volume of the H2O liquid. Now, the volume of the CO2 is going to be the same, right? This should be 148.2 liters, because both of these are ideal gases. Now, the volume of H2O, we have 2 choices. We could look up the density at 25 degrees C, or we could do it to 2 decimal. Okay, so if to 2 decimal places, the density of water is 1.00 grams per milliliter. To more, we have to look it up. I looked it up the other day. At 25 degrees C, the density of water is 0.9970 grams per milliliter. And so it depends on what we want. You know. Usually we just do it to 2 decimals, right? Because it's not worth looking up. And so if we do it to 2 decimal places, then we had 6 moles of water, 6 moles of H2O liquid. Let's see what difference it makes. If we did 6 moles of H2O liquid, and we know it's 18.02 grams per mole, which means, we'll just do this one first, then 1,000 liters per liter. And so I get 6 times 18.02 divided by 1,000. And this comes out to 0.1081 liters. Now, or we could do it with the same thing, except let's use a more accurate density. More accurate density with 9970 grams per milliliter. This is the actual density at 25 degrees C, just to 4 sig figs. So divided by 0.997, and I get 0.1084 liters. So take a look at the difference here. With the more accurate density, is it really going to make much of a difference in our calculation? Not really to the number of sig figs we're allowed. When we round this, it rounds to the same number. And so it didn't make that much of a difference. However, if we want more accuracy, then we would do this one here, correct? Now we have the volume. So let's see what the volume is here. And so this is 148.2 plus 0.1 gives us a volume of 148.3 liters here. And so do you see in other words, when we do this calculation, delta B is equal to pretty much 0, right? Because we start at 148.3, we ended up at 148.3, we got 0 change. That's because the density of water, you know, we form about 100 grams of water. The density of water is about a gram per milliliter. Well, the density of glucose is roughly the same, you know, which is 1.5 times that of water. Right? And so again, we got no volume change. But what we're going to do now is we're just going to do a highly, as accurate as possible, because there's got to be a little bit of volume change, right? Got to be a little bit of volume change, and therefore maybe a little bit of work, you know. And so what we're going to do here is we'll just do a more accurate calculation, saying that O2 and CO2 aren't equally ideal. You know, CO2 is less ideal than O2. And so the next calculation is we're going to treat the gases as real. What was it? Did I do ABC? Or did I do 1, 2, 3? How did I number these? All right. Now we're going to try real gas instead. And so here we'll just repeat the calculation, except we're not going to. And so the volume initial is just the volume of the glucose plus the volume of the O2. What did we get last time? Can you, well, the volume of the glucose we just did, that was point, I just erased it. Can you remind me what it was? 0.1? 111?
116.
116? 1 liters. Okay, and the volume of O2, what did we calculate after all that work the other day, yesterday, using the van der Waals equation? What do you calculate? Like 147 point. Well, yeah. 148.65. Is that what we got from successive approximations?
Oh, no.
Or is that the total? Oh, that was the total?
148.6.
148 points. What was it?
0.6.
0.6. Was that what we got from successive approximations? 148.6? No, that was the total?
Yeah.
It was the total. Ah, that's all right. It's in your notes. You should review your notes and sort it out. One of the things, you know, that I've found very effective, and this is it. The way to really remember the material is, and this is what's typically done because way to really learn the material is to sort things out in your own mind, you know. Don't have the instructor sort things out for you, but you do it yourself. You go back through and you organize all the information. When that process of organizing the information really makes it stick in your memory versus memorizing. Yeah, have you ever like memorized flashcards and found it very difficult to remember, or memorize by sight, or memorize things, you know, or memorize a passage? When you memorize it's very difficult to remember things. This is what I found. But you know, when you had to do something, like when you wrote the passage yourself, you know, it's much easier to memorize. Well, you aren't going to write chemistry by yourself, but you're going to, you know, the next best thing is take the information and sort it out. And so you'll have a jumble of numbers from our last calculation. What you need to do is sit down there and sort things out, you know, figure it out, and then it really sticks in your memory. But anyway, we have this final number, 148.6 was it? Okay. And then we have the water, which is 0.108. So let's calculate the volume of CO2. So the volume final is going to be the volume of the CO2 plus the volume of the water. So we just did the volume of the water. Let's do the volume of the CO2. The volume of CO2, if we assume it's going to have real properties, then we'll have to go back to chapter 6 and get the information for CO2. CO2 is going to be less ideal than O2 is CO2. So we have the data there. So let's go ahead and figure out the volume of the CO2. The volume of CO2, this is what we're going to calculate. Well, we know that we have this. The pressure is equal to N squared A over V squared. V minus NV equals nRT. All right, so the pressure is 1 bar. N squared A, well, A is different for CO2, so we'll have to do it for that. Again, I'm going to ignore the units. As long as the units are consistent here, the units should work out. I'm just ignoring the units because for clarity here. 3.658 in our algebra calculation times 6, 21.948. So this is going to be 21.948 over V squared, V minus NV. So 6 times V for CO2, 0.0429. 0.0429. So this is 0.2574 is equal to nRT. nRT, does somebody have that written down from earlier? 146.723. All right. Is that what other people had? 146.7?
I didn't use 115 for Kelvin.
Okay. Well, actually, maybe let's see. Well, we have to figure out the first volume. You know, we need a guess. So we're just going to, you know, our first guess is going to be it's close to ideal. And so this is the volume for an ideal. Volume for an ideal is equal to nRT over P. P is just 1. And so let's just go ahead. 6 times 0.08206 times, we got to convert it into bar, 1.01325 bar times 298.15 equals 145.38. 145.38. Is that, did I do that right? Let me just double check this. This is 0.6 moles, right? R 0.08206 liters atmosphere per mole Kelvin. Got to convert this. This 1.01325 a bar per atmosphere. Is that right? Or is that atmospheres per bar? No, that's bars per atmosphere. So bar is a little bit smaller than an atmosphere. That's right. Bar per atmosphere times 298.15 Kelvin divided by 1 bar of pressure. And so let me just double check it because I got a different number than you. Unless, did you do it 6 times 0.08206 times 1.01325 times 298.15. The unit should work out 148. Oh, I got a different number this time. 148.74. The reason I'm checking it is because I remember number 148, because our first guess was 149. Right. And so and so NRT is 148.74. And so this is our target, 148.74. It's our target number. What should we guess for our first guess? And so my first guess will be what? Well, 140, I guess I could put in 148.74 in there, right, and see, but I don't want too many decimal places because that means more in algebra. So my first guess is a volume is 149 liters. All right, so let's do that. And so I'll get 21.948 divided by 149 squared equals that plus 1 equals that times parentheses 149 minus 0.2574, 0.2574. And so I get this, I get 148.8 is equal to 148.74. It's a little bit high, right? Just a little bit high. So what should we try? Should we lower it or raise it? This is our first guess. And my next guess is going to be volume equals 148 liters. And so let's try that now. So I get 21.948 divided by 148 squared, because I don't know how it changes, plus 1 times 148 minus 0.2574. And I get 147.89, which is not equal. And so now let's look at the numbers here. I just want to drop this down by 10. You know, this is 148.8, this is 147.8, so this is one full unit. So I should be about 1/10 below this. Does that make sense? And so I'm going to go 148.9 is my next guess. And so my next guess is going to be V equals 148.9. Let's try that. Meters. So I'll get 21.948 divided by 148.9 squared equals plus 1 equals times 148.9 minus 0.2574. And so I get a 148.78. 148.78, very close to 148.74, just slightly off. I want to drop that down just a little bit. Just a little bit. And so I could try a volume of 148.8. Let's try that and see where that gets us. And so I'll go 21.948 divided by 148.8 squared equals that plus 1 equals times 148.8 minus 0.2574, parentheses, 148.68. 148.68. I want 0.74 as my target, so where am I? This is about 10, right? In fact, this is 10. So if I want 7.4, then I got to go 6 above this, 4 below this. So 6 above this, 4 below this. So 148.86. Do you see? What do you think? Yeah? If it's linear, we're assuming it's linear. It's not, but if it's linear, that's where it should be. And so let's just give it a try. This is going to be 21.948 divided by 148.86 squared plus 1 times parentheses 148.86 minus 0.2574. 148.749. 148.749. I want 148.740, even though we don't know if it's a 0 or not, but let's just try to get a little bit closer. Because this would round to what? If I had to round this, it would round to 148.75. I don't want that. And so at least get it to round to 148.74. And so I'm just a little bit too high. So let's try 148.85. Try that. And so this is going to be 21.948 divided by 148.85 squared equals that plus 1 equals that times 148.85 minus 0.2574. 148.59. 148.59. I want way too high. And so let's take a look at the numbers here. So 59 to 74 is 60, that's about 14. So I just need to drop it less than a half. And so what I'll do is I'm going to go like this. I'm going to go much closer to this. 148 point, let's try 859. What do you think? Let's go for that and see what happens here. Now, you know, we can wait until it converges, but you see what's happening is we're adding an extra decimal place each time. As we continue to add the extra decimal place, then pretty soon you're going to reach a point where you're adding so many decimal places, it doesn't matter, we got to round those off anyway, right? And so in this case, we are already okay to stop. We could have stopped here because this additional decimal place is not going to impact it. Right? However, we just look and now, are there quicker ways of doing this? There's much faster way. I mean, one, you could just do this in Excel manually. Two, there's actually programs that do this. You know, which would, in Excel, you can make a program, or you can. So you can program this to seek. And three, there's lots of programs that do this. You know, a lot of mathematical programs will do this. You know, because to get an exact answer, you know, and that is this. Is this an exact answer? This is not an exact answer, but in math you're supposed to get exact answers. But in science we don't. In science we have to do approximations all the time. In fact, all calculations that you do in science are approximations. And so this is the difficult thing. The difficult thing is this. Somebody is going to ask you what kind of error is introduced in your calculation by making these approximations. And the problem is that a lot of people can't answer that. They don't know numbers. All right. And so, you know, mathematicians would be driven crazy, but they want to do this exactly. You know, they don't want an approximate answer, they want the answer. And so, let's try this one, 21.948. If I was doing this on my own, I would just do this in Excel and I'd have the answer in seconds. But to show you guys, .859. I'm showing you guys because this is about as much time as it should take you. It doesn't take that much time. Times 148.859 minus 0.2574. And I get 148.7487. Well, oops, 7487. And so it's still 148, we want 148.74, so it's still too high. And so I think I didn't change it enough here. And so we just dropped down from 490 roughly to 487. There's barely any change. And so let's try one more, 148.85. What do you think?
I think I got 148.739.
You got 739? Oh, did I screw up the calculation? 148.739? Is that what you guys got? Okay, I must have miskeyed it. 739 then is, this is perfect then. This rounds to 4, this rounds to 5, and so this would be it.
That was for 148.85.
Oh, 85?
Yeah.
This
Yeah.
one?
Yes.
You got 148.739,
739.
so this, I screwed up this calculation, 739. All right, we could stop here then. We could stop here because it's 148.74 essentially. And we did it. How many guesses did that take? 1, 2, 3, 4, 5, 6 guesses. That was easy. It was easy. On the computer programs, what happens is it starts to compile. And what happens is it might not hit a convergence. If it doesn't hit a convergence, then it just keeps compiling. And so we'll go on and on until you kill the program. Hopefully it converges and finds something. All right, so now we have it. We didn't assume ideal. How does this compare to the O2? You know, what was the volume of the O2? Can someone just look up the volume of the O2 for me? Yeah. From yesterday? You guys review these calculations? One of the other things you'll find very beneficial is this. One thing I notice a lot of beginning students do that advanced students never do. A lot of beginning students, they don't do the calculations given in class by themselves. You know, they have in their notes and they just look at it, but they don't actually try it themselves. And the thing is this, you know, the way I think of this is this analogy where, let's say you're visiting some Central American jungle. And so you're following a guide through the jungle, and the guide knows exactly where to go, you know, which path to take, what to do to get to the destination. And so the next day you say, I don't need the guide, I know how to go. I was able to follow the guide, no problem. And then you go out in the jungle and all of a sudden you get lost, you know, because there are lots of different paths you didn't see. Of course, the guide didn't mention anything about those paths because they knew what paths to avoid. And so the point of this story is that you can't learn by watching somebody do it. You have to do it yourself. If you never go back through those calculations, you're really shooting yourself in the foot. You're really giving yourself a great disadvantage. because, and it's not just beginning students, because there are stories of advanced students doing the exact same thing. But watching somebody do it and doing it yourself are two totally different things. Somebody doing it themselves is unlikely to make any mistakes because one, it wastes time, and two, they know exactly what to do. But somebody doing it themselves for the first time, they tend to make a lot of mistakes and have to go back through it. And so those are the other paths. And so what was the volume of the O2 we calculated yesterday? One of the reasons, I told you I don't like PowerPoints. I don't like PowerPoints because, one, it's too hard to write notes, you know. Usually people go through PowerPoints quite quickly. Two, if you print them out, then you aren't writing. Writing is a whole thing, you know, of organizing the information in your own words and learning the material. Unless the concepts are very simple, and which a lot of PowerPoints are, it's just simple, not that much information. Because when there's too much information in the PowerPoints, then people tend to not like those. Did anybody write it down?
Without the success of approximation?
No, with the successive. We did in 3 guesses.
I used the calculator after.
Oh yeah, I know. You just programmed it. I mean, whatever. Somebody tell me. I don't want to do it again. See, now you have to think about this because let me tell you, one thing I noticed at the UCLA was I wasn't a pre-med, but I noticed that 80% of my class were pre-med. And it's very competitive, pre-med students, because it's very hard to get into medical school. A lot of them wanted to get into medical school at UCLA. They wanted to undergrad at UCLA and get into medical school at UCLA. They're going to take whatever it took to get into medical school. Everybody asked me, is the class going to be curved? You don't want a curved class. If you see the curve at UCLA with all those pre-meds, then you could be getting like, you know, a high B and still end up with a D in the class because of the curve, you know. So, of course, if the curve favors you, that's good, but oftentimes the curve will not favor you if you just want to, you know, get through the class. So, this kind of stuff you should have in your notes. Otherwise, I'll just throw everything on the PowerPoint and bother writing it out.
Oh, I tried solving for it and I got 148.6.
148.6. Okay, thanks.
Came out to 148.7 for
742
2.
was the total volume. What was the volume just of the O2?
It's 148.6.
148.6. Give me one more digit.
Okay.
All right. So the volume of the CO2, since CO2 is not as ideal, it's not going to give us the same volume. The volume of the CO2 is 148.85. That's what we got, liters. And so you just redid the calculation for the O2 at 148.6. We'll just go with that. And so take a look at the difference in the volume. We expect some volume difference because CO2 and O2 are going to have different volume, so particles, which is B, and they're going to have different strengths, intermolecular forces, which is A. And so you can see that. we get a slightly different volume. All right, and so let's redo the calculation quickly. What was the volume of the glucose? It was like 0.1008 or something like that. And so the total volume here is going to be 148.7. And the volume of the H2O was 0.1 something something. So this is going to give us a total volume of 148.9. Actually, what was the volume of the H2O? It's 0.1. 108. And so I need to do that because I carried this one out a little bit farther. And so this is going to give us 148.958, which is going to give us, let's round it. Oh, actually, let's not round it.
So the value of glucose is 0.117?
0.117 for the H2O?
No, glucose.
Or for glucose? Oh, 117, thanks. And so this is 7.1. And so we'll just carry up like some extra digits. We have to carry extra digits because the volume change is very small. If I round this to 149 and round this to 149, then delta V is equal to 0. So I need to carry some extra digits so we can see what this tiny change in volume actually is. And it is a pretty tiny change in volume in terms of liters. In terms of milliliters, it's a much more significant change in volume. And so what is delta V here? Well, delta V is, well, it looks like the volume expanded a little bit. And so we'll just do it rough, 0.248 liters, something like that. You know, we'd carry extra digits if we needed. All right, and so the work involved in this is equal to P delta V. And so this is going to be 1 bar times 0.248 liters, which is going to give me 0.248 liters a bar. And then we'll multiply it. And the conversion here is that it's actually, because of round off error, it didn't come out right, but the conversion is actually 100 joules per liter bar. And so this is going to be times 100, which gives us 24.8 joules. Is that correct? 24.8 joules of work. So I didn't, all right, now the volume increased, right? So this is minus P delta V, and so this is going to be a loss of energy, loss of 24.8 joules. And the volume expanded slightly. Okay. And so that means that delta U is going to equal delta H plus W. Delta H is minus 2,000. What was it again? 2008.5? 2008.2?
802.5. 2802.5.
2802.5, thanks. 2802.5 kilojoules. And then we have to add that many joules. So this is going to be plus or minus. Actually, I did this wrong. Did I do this right? Yeah. Plus or minus 24.8 joules. And then we'll have to convert that into kilojoules, which is going to move the decimal 3 over. And so this is going to be minus 2802.5248 kilojoules. So we calculated the work. Was the work all that significant? No. There was a little bit of work done, but it wasn't that significant. It wasn't that significant because, well, it is significant. It is significant because the volume expanded by, 24.8 milliliters. A volume of expansion of 24.8 milliliters. That's going to require a little bit of work, right? To blow up a 25 milliliter balloon. But the reason we call it insignificant is because the energies, the amount of energies in chemical reactions is huge. It's not that the work is always insignificant. For example, if this term were 0, then would the work be significant? Yes. The reason we say that the work is insignificant is because this term is so huge. That's like this. You know, if you're a billionaire, then is $10 all that significant? No, but if you're panhandling in the streets or something, then $10 is significant. And it's still $10. This is still 24.8 joules, right? But when we say it's significant and when we say it's not significant, it depends on what we compare it with. And so let's say a drop of water, liquid water on Mars, maybe that's, you know, significant. Or on the moon, you know. But a drop of water in a swimming pool, is that significant? No, but it's the same thing. It's a one drop. And so this is how we think about numbers in science. We think about what we're comparing it to, and then thinking in terms of significant or insignificant. And so 10 to the minus 20 joules. 10 to the minus, let's go 10 to the minus 18 joules. Significant or insignificant? Tell me. 10 to the minus 18 joules, significant or insignificant? The correct answer is it depends on what you're comparing it with. If you're comparing with a hot cup of coffee, 10 to the minus 18 joules, significant or insignificant? Totally insignificant. If you're comparing it to a single hydrogen atom, significant or insignificant? Hugely significant. 10 to the minus 18 joules is the amount of energy it takes to rip an electron off a hydrogen atom. And so you'll create a hydrogen ion. And so 10 to the minus 18 joules. And so the same thing here, you know. Yes, we want to figure out what that work is and then figure out is it significant or insignificant. And that's numbers for you. All right, that's the hardest part. You know, the calculation is often the easy part, unless you know, even with the successive approximation stuff. The calculation is the easy part. The hard part is interpreting the numbers, which a lot of people aren't able to do. And so interpreting the numbers means, do we have to do the van der Waals, or can we be okay with the ideal? You tell me. Should I worry about doing the van der Waals calculation or not? Well, it depends. The answer to that depends on the conditions. And so the conditions, you have to have a little bit of experience. But if you read this last section of chapter 6, then I'll tell you when it becomes significant. We definitely have to calculate the van der Waals when we're at very high pressures. Because what happens is, at very high pressures, we have enormous deviations from ideal behavior, which is the black line. So when we get to about 100 atmospheres, take a look, CO2 is way up. If you, in fact, the ideal gas law is totally worthless at 100 atmospheres for CO2. Now for helium, it's a little bit better, but still, you know, and hydrogen, helium is even better than hydrogen, but O2, you know, at 100 atmospheres, we're looking at huge. And so basically, the only place the ideal gas law is okay is right at the beginning. Right at the beginning is very low pressure. It's between 0 and, let's say, 10, 0 and 20 atmospheres. But beyond that, then using the ideal gas law is a waste of time. Okay, that's number one. Number two is at very low temperatures. If you're at low temperatures, then what happens is gases don't stay gas. They liquefy. So if you did an ideal gas law calculation for steam at minus 300 Fahrenheit, is that going to work? No, because the steam is going to be a solid block of ice. Well, anyway, here. Did somebody forget this yesterday? Does it look familiar? No. All right, let's go next. All right, that concludes chapter 7. Any questions on chapter 7? What we're going to do now is go on to chapter 8. And let me just do this. I tried this yesterday. Hopefully this thing launches this time. All right. Light. Light is what we'll call electromagnetic radiation. Electromagnetic radiation is this transfer of energy in the form of electric and magnetic fields. And we have different kinds of light. We have radio waves, which is invisible light, essentially light. We have microwaves here. Oh, this is hard to see. We have infrared, visible light, ultraviolet, X-rays, gamma rays, different forms of light. I think I screwed this up. And so let's take a look at the PowerPoint here, which I think I downloaded the other day. And so what does light consist of? Essentially waves, of, but not like these string, this kind of wave, these traveling waves. What we have is this wave here, and the wave consists of an electric field, let's say, this red line. An electric field, when we think about an electric field, you think, normally you think positive, negative, right? And so this is what's happening. This wave is traveling through space. This wave is traveling through space at the speed of light. If this wave hits you, what do you feel? If this wave hits you, what you feel is you feel an oscillating electric field. An oscillating electric field would be something like this. It would go plus, minus, plus, minus, plus, minus, right? And so you'd see plus, minus, plus, minus, plus, minus, that kind of thing. Plus being like positive charge, minus being like negative charge. That's what you'd feel. You'd also get hit with a magnetic field. What would the magnetic field feel like? So electric field, let's say it's like this. The magnetic field is like this. This would be polarized, we would say. If you got hit by a magnetic field, what would you feel? Well, it's a wave. And so this wave is traveling at you at the speed of light. So what you feel is north, south, north, south, north, south. And it'd be oscillating like that, north, south, north, south. And so magnetic fields would interact with magnetic objects. If you had a little magnet, what would happen if it got hit by that wave? If you had a little magnet, it would see north on this side, and then all of a sudden south. So the magnet would have to flip like this, oscillate with the field. That's with a little magnet, but we're not going to concern ourselves with the magnetic portion of the field. We're going to really look at the electric portion of the field. And so what interacts? Like say, for example, what would interact with a plus minus like this? Plus minus. So you want to make an antenna. We'll make a good, let's say you have an old car, the car antenna broke. The car antenna broke off your old car, and I don't know, I don't see this that much anymore, but I used to see people put a metal coat hanger on their, have you ever seen that, metal coat hanger? I don't see that often because, but I used to see a lot. What about a plastic coat hanger? Why not a plastic coat hanger? Why a metal coat hanger?
It picks up the waves?
It picks up the waves, right? And the wave is going to be what? This oscillating electric field, plus, minus. What in the metal interacts with that wave? Well, when we think about it, we think about electrical interactions, it has to have a charge, right? One. And so we have two things that can interact with an oscillating field in a metal. We have the nucleus, which is positively charged. Do you think the nucleus is going to ride the wave like a surfer? Plus, minus, plus, minus. It turns out the nucleus doesn't. The nucleus is kind of heavy. It's got some inertia, Radio waves are kind of weak as far as waves go. And so the nucleus isn't really going to interact with that wave. How about the electrons? Do electrons have much inertia in that sense? Are they heavy, hard to move? No, electrons are very low mass, very, very light in that sense. And so electrons, if it's plus, it'll be attracted. If it's minus, it'll be repelled, right? And so what happens is, as the wave comes along, the electrons will start to ride the waves like a buoy, up and down. And so electrons are going to be doing this. And so when we look at electromagnetic radiation, we have different types of electromagnetic radiation. Electromagnetic is electric and magnetic fields radiation. And this radiation is moving at the speed of light. It's very fast. So all light moves at the speed of light, which is given by c. c equals the speed of light. Do you know how fast it's moving? A vacuum? In a vacuum, it moves at 2.998. Just go with 466. 2.998 times 10 to the 8 meters per second. It's extremely fast, the speed of light. 30 million meters per second. And so it's moving very fast. And so let's take a look at the different forms. We saw radio, we saw microwave, we saw infrared, we saw visible, we saw ultraviolet, and we see gamma. These are all different forms of light. And the difference is in terms of energy. Here. Radio and TV waves will have low energy. And as we go up, we'll get higher energy. The energy is going to be a function of this wavelength and frequency. So wavelength and frequency, wavelength is given by the symbol lambda, frequency is given by the symbol mu. And so all these are moving at the same speed. The difference is in terms of wavelength and frequency. So radio waves have what we call long wavelengths. These are very long wavelengths, like kilometers long. And a wavelength is a peak to peak. So as the wave moves, you're at the top of the peak, the wave passes you, so you go into this trough, and then you go back up to the top. That's one full cycle. Call it. For gamma rays, the wavelength is much shorter. And so this is lambda for gamma rays. It's a short wavelength. Since they're both moving at the same speed, gamma rays and radio waves are moving at the same speed. What happens is this oscillation. This oscillation is called the frequency. And here, the radio waves oscillate at lower frequencies, like kilohertz or megahertz, whereas gamma rays oscillate at extremely high frequency, extremely, that I don't even know the metric prefix for it. But radio is easy because kilohertz is AM, megahertz is FM. And what a hertz is this, like let's say megahertz. A megahertz is 1,000,000 hertz. A hertz is this. A hertz is an HZ, and that's 1 cycle per second. And so it's 1 oscillation cycle per second. And so megahertz would be 1,000,000 oscillations per second. And so the radio wave has 1,000,000 oscillations in 1 second. Boom, 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 boom. That's very fast. But microwaves are a little faster, but when we get to gamma, it's crazy. The number of oscillations per second, the frequency, is huge. That we don't really have a metric prefix that easily does that for us. And so if you're an electron, this is what you see. With radio waves, you see this. For gamma rays, you'd see this. You know, it's oscillating like crazy. Right. And so that's what's going to happen. Now, when light interacts with matter, it's going to react with charged particles because light consists of electric fields, right? And so we need some kind of charge to interact with this. And so let's take a look at light and matter. Radio waves are enough to excite electrons in metals. And so excite electrons in metals. The electrons in metals are kind of loosely held, right? This is why plastic doesn't work. You know, electrons in plastic are tightly held. It takes a lot of energy to excite them, which radio waves don't have enough energy to excite electrons in plastic. Microwaves can overly excite electrons in metals, right? You ever put metals in microwaves? Like, have you ever put aluminum foil in a microwave? Probably. But the electrons in aluminum foil get overly excited in the microwaves, don't they? Have you seen what happens? Sparks, right? Lightning bolts with electrons. And so microwaves, yeah, we'll say overly excite electrons in metals. But is that the only thing microwaves do? Well, they'll interact with any charged species. So if you have a water molecule is charged. Well, a water molecule is neutral, right? But a water molecule does have charge. Because if we look at it, one of the biggest uses for microwaves is to interact with water. Water has a charge of delta minus and delta plus. One end of a water molecule is a negative charge, the other end has a positive charge. So if you're an oscillating field like this, the water molecule should do this, right? It should flip with the field because on one end it's negative, on the other end it's positive. And so what microwaves do is they rotate small polar molecules like water. So rotate. That's all they have enough energy to do is rotate. But it turns out it requires a very specific energy to rotate a water molecule. It's not just any energy. You know, you can't just, I'm going to rotate it slowly or rotate it quickly. It turns out that you need a certain amount to get it to go over the hump and rotate. And so it rotates small molecules. Infrared vibrates polar molecules. And so in water we have a delta positive end and a delta negative end here. And so what happens is this. As infrared comes, let's say this is the IR here. We're looking at positive, negative, whatever. When we look at a bond is, let's say an HO bond is like this. An HO bond. One end of the bond is negative, the other end is positive. And so what happens is it doesn't flip with IR. You know, with microwaves, you could flip this. With IR, or rotate it, we call it. With IR, what happens is this thing will oscillate with the electrons in this bond. So we got more electrons here towards more electron density here towards the oxygen, less electron density, what we call, towards the hydrogen. And so this is more negative. So the more negative. So what happens is this electron cloud goes starts to oscillate. In other words, the bond starts to vibrate with IR. However, things like oxygen. Does oxygen have a polar bond? Oxygen does not absorb IR, nor does nitrogen. Nitrogen, these are invisible to IR. They don't vibrate. These are what we call non-greenhouse gases. Oxygen and nitrogen, that doesn't contribute to the greenhouse effect. Whereas if you had water vapor, if you have water vapor in the room, the higher the humidity, the more it will feel like a greenhouse, wouldn't it? Because water absorbs infrared radiation, which is just heat. We think of infrared as heat. And so these don't. What other things? Well, methane is a greenhouse gas. CO2 is a greenhouse gas. Water would be a greenhouse gas. And it keeps them warm. Visible excites electrons in matter. You know, the more tightly held electrons. It might knock them off, you know. A visible light, you just excite it. So let's say some visible light's passing through like this, and it couples with electron, and the electron starts to get excited. Like that. Ultraviolet, I forgot one, X-rays. Ultraviolet, X-ray, and gamma rays. Ultraviolet, you know, what happens is, you know, IR comes in here and starts vibrating this. And visible could come in here, although the electrons in water are really excited by visible light. Water's kind of invisible to visible light. But ultraviolet breaks bonds. This excites the electrons in the bond so much, it breaks the bond. So ultraviolet has enough energy to cause bond breakage. An X-ray and gamma ray, this is called ionizing radiation. Do you know why it's called ionizing radiation? The reason it's called ionizing radiation is because X-rays and gamma rays can excite the electrons so much that, boom, the electron gets knocked off. And we create ion. And so it ionizes matter. So gamma rays and X-rays will ionize matter, that is, excite electrons so much it will get knocked off. Ultraviolet can ionize matter too. Ultraviolet is enough to ionize hydrogen atoms. So the relationship here is this. If we look at this, that is, the frequency is inversely proportional to lambda. So the longer the wavelength, the lower the frequency. Is that right? Yeah. And the shorter the wavelength, the higher the frequency. So this frequency. The units of frequency are hertz there, you see. So hertz, we usually get rid of the cycle and just say per second. The units of wavelength are here. These are the common ones: centimeters, micrometers, nanometers, angstroms, and picometers. Those are common units for wavelength. Let's take a look at some of the frequencies. I told you that radio waves are going to have around megahertz frequency, which would be a 10 to the 6 hertz. And the radio waves are megahertz. What are gamma rays? What would you call that? What's the metric prefix for 10 to the 22nd? Do you know? I don't know either. So what we do is, what's faster than a megahertz? Gigahertz. Gigahertz would be 10 to the 9th. Well, gigahertz, we're starting to get into microwaves. You know, 4.5. Have you looked at your cell phone? What's the frequency? 4.5 gigahertz? Starting to get into microwaves. Gigahertz. And so giga would be 10 to the 9th. What's faster than giga? Do you know? terahertz, is that right? All right, terahertz would be 10 to the 12th. Well, what terahertz were in the microwave region? Your microwave probably operates at, take a look at your microwave, the operating frequency. I think it's 4.5 gigahertz, your microwave. Should be right around there. So we're at terahertz. So terahertz is 10 to the 12th, right? Is that right? And that takes us into infrared. And so 10 to the 12th would be a tera. A tera would be, take us over here. So it would be a terahertz, be gamma ray, extremely high. Well, that's one way of characterizing. Sometimes we characterize by frequency, sometimes we characterize by wavelength. By wavelength, we often use microns for infrared because it's at 10 to the minus 6 meters. 10 to the minus 6 meters is microns. Right? For visible light, do you know what we use for visible light? We use nanometers because visible is 10 to the minus 7 or hundreds of 10 to the minus 9, which would be nano. For ultraviolet, oftentimes we use wavelength. But let's look at the wavelength. The wavelength goes from 10,000 meters, 100 meters, 10 meters. Look at, if we're at megahertz, then we're looking at wavelengths on the order of a meter. It's huge. And so it's a meter wavelength, which is this, a meter wavelength, but we get 1 million of these pass by in 1 second. That's moving fast. Okay, then over here, look at the gamma rays. It's 10 to the minus 14 meters. 10 to the minus 14 meters, how big is an atom? How big is an atom? An angstrom, 10 to the minus 10 meters. An atom's about this big. This is smaller than an atom. The wavelength of that. It's smaller than an atom. All right, so it turns out most of the electromagnetic spectrum is invisible to our eye. The only part of the electromagnetic spectrum we can see is this small range. This small range we should memorize. The small range is from 390 to 760 nanometers. 760 nanometers is long wavelength. This is low energy visible light. Lower energy visible light is red. Do you know the color of the rainbow? Red. Everybody know it? Okay, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And so at 760 we start off with red. At 390 we end violet. Okay, on the other side of red is what we call, on the other side of red is called infrared. On the other side of violet is called ultraviolet. And so ultraviolet would have wavelengths less than 390. Infrared would have wavelengths right here. 1,000 nanometers is a micron. And so infrared is in the 1,000 nanometer range, which is the micron range. And infrared goes into the lower triple to double digits of the nanometers. I mean, not infrared, ultraviolet. All right, these are waves, and waves can interact. You know, waves interact with each other, and we get interference and in other words, we can have two types of interference. We have destructive interference, where a wave can cancel out, like noise canceling headphones or something like that. And then we have constructive interference, where the waves can build up on each other. And we can see this kind of interference pattern here when these two waves come here. These interference patterns are what we saw in the spectroscopes. In the spectroscopes, we have what's called a diffraction grating. Diffraction grating has a whole bunch of lines in here, and it depends on how the light hits these. Different wavelengths of light. We see different wavelengths of light because all the other ones are destroyed by destructive interference. And so this is it. Prisms will also separate out the light. And so based on this constructive, destructive interference, we get things called refraction grating, in which we could take white light, although this is not purely white light, we can take white light and spread it out into the colors of the rainbow. So we'll see red, orange, yellow, green, blue, indigo, violet there. Here it is, where we can see some constructive interference, in which these two waves, they interfere constructively, because if you look, their peaks match, the troughs match, the amplitudes come from here. Whereas here, this is destructive interference. If the peaks and troughs are misaligned, like here, I have a peak and a trough here, these two waves are going to cancel each other out. If they're slightly mismatched, they cancel each other out. Or fully mismatched here. Here we have refraction of light. Refraction of light just takes advantage of what? People know how refraction of light spreads out. This is white light hitting the prism. Refraction of light just takes advantage of different speeds through different medium. I told you the speed of light is about 3 times 10 to the 8 meters per second, but in a prism like this, they don't all move at the same speed, essentially. And so it spreads out. And if you look at this, you look, which one is more? Well, it looks like violet, right? Impacted, whereas the red is less influenced by that. So, so white light consists of all the colors of the rainbow. You can see it with the refraction of light with water droplets here. The diffraction grating we'll look at again in chapter 12, so I'm not going to talk anything more about that. Here you can see some molten iron producing, what does that look like? White light right there, right? White light. We want a nice white light bulb. You can see, if you're going to use a light bulb in your room, you probably want to use something that gives you something close to the solar spectrum, maybe. The fluorescent lamps, did those look like the solar spectrum? Yeah, yes and no. The light bulb that we saw earlier, the incandescent light, was pretty good. And so this would make a good one too, but the problem is once this cools down, is it going to stop? Continue emitting light. And so this molten iron is essentially a light bulb. How does a light bulb work? If you keep pouring this in a darkened room, you're going to get a lot of light, And so let's block off all the windows. This room's going to light up from this because the molten iron is emitting light. What causes molten iron to emit light? Yeah. What happens is iron has a lot of loose electrons, especially molten iron. And so what happens is these electrons get excited. They're getting excited by the heat here, a lot of collisions and vibrations and whatever else. So as electrons get excited, they don't stay excited forever. Eventually they're going to relax back down, but energy is conserved. When these excited electrons, the system, loses energy, then that energy is going to go into the surroundings. Normally we think of the energy going to the surroundings as heat and work. Well, is light heat? Well, heat is this transfer of kinetic energy, or vibrational kinetic energy. Light is work. And so this light that we're generating here is just energy being emitted. And so we can make a light bulb out of anything. It doesn't have to be molten iron. If I take this stainless steel spatula, it's a nice, clean, new one. I only have nice, new ones. So you guys can make a light bulb too, right? We just got to excite the electrons. Electrons aren't going to stay excited forever. One way of exciting electrons is just heat it up. So eventually, as I continue to heat this piece of metal, it's going to start to glow. You've seen this, right? It'll start to glow. This is not a good flame. It's taking too long. First it'll glow red hot. And a red hot piece of metal. If I had a spatula, it'd be better. This is too big. It's going to start to glow red hot. Do you see it starting to glow a little bit? And as it gets hotter and hotter, like if I flip off the lights, maybe that'll be easier to see. Let me flip off the light. Okay, actually that was good. Do you see it glowing red hot? It's red hot. Don't touch it. Eventually I could get this to glow white hot if I get it hot enough. When it glows white hot, then it's emitting all the colors of the rainbow. Fortunately, this is stainless steel, so stainless steel is hard to oxidize. If this were just a piece of iron, then it'd turn quite black, and I'd be forming iron oxide on the surface. So I can make a light bulb just out of a piece of metal. In fact, that's what that light bulb was made out of. The light bulb that I used the other day was made out of tungsten. There's tungsten metal in there. And what happens is you just heat up that piece of tungsten metal until it gets very hot and starts emitting white light. Okay. And so you got that piece of tungsten metal, and how do you get it hot? Well, you pass an electric current through it. Pass that electric current, there's some electrical resistance, it starts getting hot. When it gets hot, then the electrons get excited and start emitting light. So essentially, you can make a light bulb out of anything that contains what? You should be able to make a light bulb out of anything that contains electrons that can be excited, right? Anything. And so we should be able to make a light bulb out of anything. So let's try to make a light bulb out of something next. Oh, I gotta stop. We're out of time. What lab are we doing tomorrow? 4? Okay, 4. Yeah, just read through the lab there. We're going to use a different kind of spectroscope, so the instructions are going to be different. We'll just come up with some rough outline in your mind for tomorrow's lab. Yeah.
For tomorrow's lab, would, because I'm colorblind, and would I have a hard time for
No.
doing an experiment?
No, not at all.
Okay.
You don't have to see any colors.
Not recording colors and all that stuff?
We're going to record the colors, but we're going to use an instrument to record the colors. So
Okay.
we're just going to get a spectrum, which just is a graph showing what colors are.
Okay. All right.
From there.
That's thank you.
Can you explain number 11?
Heat, is it a state function or a path-dependent function? Heat. What's the difference between a path-dependent function and a state function?
Isn't a state function?
Heat is not a state function. Heat is a path-dependent function. So know those two definitions. Go back in the book and look
Okay.
at the difference between a path-dependent and a state function. Okay.
Was he not, do we have to turn in something this week?
Yeah. Experiment 2.
Tomorrow or today?
Tomorrow.
Tomorrow. Okay.
Oh.
You just want to do that, show me that.
Oh, yeah.
Do
Okay.
the exam, the ones,
All right.
and I can get the ones that. Yeah, it's 18, 28. You said just
Oh, yeah, okay, can you show that to me tomorrow? Because I need the computer to change it. Computer in the lab, I can change that. So fix that.
I keep forgetting to ask you.